Section 2.4, set applications. I'd like to start off looking at our notes here. Let's assume there are 15 players on the CRC men's basketball team, and there are 20 players on the CRC men's baseball team. If the two teams went out to dinner together, does that mean there would be 35 players total? There's 15 players on one team, there's 20 players on the other. Well, 15 plus 20 makes 35. Is it for certain there would be 35 players total? Of course it's possible, but you gotta be careful. What if some of the players on the basketball team were also on the baseball team? Then do you understand it would be less than 35 players total if we put the two teams together? You got to be careful of situations like that. And when you're putting two groups together, you have to be careful of double counting. Just because there's 15 on one team and 20 on the other team and you put them together doesn't necessarily mean there's going to be 35. There very well could be 35. But if some of the players are on both teams, if some players are on the basketball team and they also happen to be on the baseball team, then it's not going to be 35 total. We don't need to double count those players. So it brings us to the big formula we learned for today. It's called the inclusion-exclusion principle. And it says for sets A and B, if you're trying to find the number of elements in A union B, you can take the number of elements in A plus the number of elements in B, but you need to be careful because you might have just double counted some people. You might have counted some people twice here, those people who are in both A and B at the same time. So we have to fix that double counting by subtracting the number of elements in A intersected with B. So the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B, because those people are the ones that we counted twice when we counted them in set A and also in set B. For a visual of that, let's look here. So objects, of course, objects in the A circle are in set A. Of course, we know that. But if we just look at the left-hand side of the A circle, not including that middle part, just look at the left-hand side of the A circle. Those objects are in set A, but they're not in set B. If we look at objects in the very middle right here, those are objects that are in both set A and B at the same time. That's the overlap. That's the intersection that we're talking about. That's the people that are on the basketball team and the baseball team. But if we look over here, this part, this right-hand part of circle B, that represents people who are in set B but not in set A. And objects on the outside of the circles, anywhere out here, they are not in either set. So when we talk about this formula, the number of elements in the union is just all of this blue stuff. All the blue stuff that we're looking at in here, that's the union of A and B. You just put A and B together. When we're looking at the number of elements in the union, we can take the number of elements in A, which would be this entire A circle, plus the number of elements in B, which would be this entire B circle. But you need to understand when you do that, we just counted these people in the middle twice. And so now we have to fix that double counting by subtracting that once. We're subtracting the number of elements in the intersection, which is that middle part. So I hope that's a good visual for the formula we have for today, the inclusion-exclusion principle. Let's recall from last section, we were looking at a math club, chess club example, kind of similar to the baseball team, basketball team that we just talked about. And I just want to remind us kind of like what we saw last section. We were noticing that the math club had 7 people. 1, 2, 3, 4, 5, 6, 7. So we could say the number of people in the math club equals 7, or the cardinality of the math club equals 7. That's another way to say that. We also noticed that the number of people in the chess club was 6. 1, 2, 3, 4, 5, 6. So I think we said something like the number of people in chess club equals 6. But when we're wanting to look at the number of people in the union of the two clubs, math club unioned with chess club, you may remember it actually was not 7 plus 6. It was not as simple as just taking the number of people in the math club plus the number of people in the chess club. That was actually not correct. Because of course, this would be 13. But that's not correct because there's not 13. If you remember, there was some people who were listed in both. Like if we're saying 13, we're counting Ivy twice. Why would we count Ivy twice? We're counting also Bree twice. We're also counting Zoe twice. So there were 3 people sort of in the overlap in the intersection of the two clubs. And if I go with 7 plus 6, which is 13, counting 3 people, we're double counting 3 people. That's why the formula we just looked at said, well, you have to fix that double counting by subtracting the number of elements in the intersection of the two sets. The intersection of the two sets would be Ivy, Bree, and Zoe, those 3 people. And now this is all correct. 7 plus 6 is 13, take away 3, that does equal 10. Everything works out now. Remember the intersection of the two sets is where do they overlap? They overlap with Ivy, Bree, and Zoe. So when we're saying that there are 3 people in the intersection, we're talking about those 3 people right there. Remember, the union of the two sets means you just throw the two sets together. You take everyone in the math club, which is Fitz and Ivy and Leon and Bree and Ted and Zoe and Nora, and you also include everyone in the chess club, which is Mia and Joe and Ivy, but we already have Ivy. We don't need to list Ivy again. And Bree, but we already have Bree. We don't need to list Bree again. Oh, and we do need to include, and also Zoe, but we already have Zoe. There's no reason to write Zoe again. So when we're saying that the math club union chess club has 10 elements, we're talking about these 10 people right here. When we're saying that the math club intersected with the chess club has 3 elements, we're talking about these 3 people right here. And this formula holds, right? 10 equals 7 plus 6, but oops, we counted 3 of them twice, so let's fix that double counting. 7 plus 6 minus 3 does make the 10. So that formula works in general. using different letters. This is the big formula for today. I'm not going to use it in every single problem today, but this is the new big formula we're going to learn today. And then we're just going to do a bunch of examples, continuing to do examples with sets and Venn diagrams and things like that. So that's what this section is all about. So just as a reminder about Venn diagrams, I know we did this last section also, but just to remind us, I'm going to call this Math Club and Chess Club. Just as a reminder, when we're talking about the Math Club, we have Fitz and Ivy and Leon and Bree and Ted and Zoe and Nora. But remember, Ivy, Bree, and Zoe are in both clubs at the same time. So Ivy, Bree, and Zoe need to be written in there in the middle. That's making sure they're in both clubs, both circles at the same time. But Fitz and Leon and Ted and Nora only are in the math club. They are not involved with the chess club, so we don't want them to be in that circle. We want these three to be in both circles. And then finally, Mia, Joe, and Owen need to be only over here in the chess club, but not in the part that overlaps with the math club. So there are 10 distinct people right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 people in the union of the two clubs. You can see that right there. When we talk about the union of the two clubs, we're talking about just anyone, anywhere in one of the circles. For the next example, let's define set A, set B, and set C in the way that we did there. And then let's try to do these three parts. This would be a good time for you to pause the video right now and work on these problems. And then come back and see how you did. So, number of elements in A union B. Let's just verify that formula that we just talked about. Let's verify the formula that we just talked about. A couple of these are pretty straightforward. Number of elements in A. Well, just count them. Here's set A. 1, 2, 3, 4, 5, 6, 7. A has 7 elements. Number of elements in set B, just count them. 1, 2, 3, 4, 5, 6, 7, 8. B has 8 elements. Those two are very simple, right? We need to think a little more about this part and this part over here. Start with the intersection here. What does A intersect with B look like? This is referring to the number of elements in A intersect B, but it would be nice to see A intersect B so we could talk about how many elements it has. Remember, A intersect B means where does A and B overlap each other? I think you can tell it's here. D, E, F, G also shows up in set B, D, E, F, G. So I think the overlap comes with those letters D, E, F, G, right? D, E, F, G shows up in set A, D, E, F, G shows up in set B. That's the intersection of the two. But there's 4 of those, right? So the number of elements in that intersection is 4. On the other side, I'm talking about the number of elements in the union of the two sets. Remember, to get into the union of the two sets, You just have to be in one or the other. To be in the intersection of two sets, you have to be in both at the same time. But to be in the union of the two sets, let's go see what the union of the two sets looks like. If you want the union of A and B, of set A and B, just list everything in set A, which is lowercase a, B, C, D, E, F, G, but also include everything in set B. But there's no reason to double count things. There's no reason to write D, E, F, G again because D, E, F, G is already there, right? So when I'm including all this stuff from set B over here, I'm not going to write D, E, F, G again. I already have D, E, F, G. I need to write H, I, J, K though. When I'm talking about the union of these two sets, there it is. Just throw them all together. But how many things are in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The number of elements in A union B equals 11. Is this a true statement? When it says verify that, it just means make sure that's true. And I think it is, right? 7 plus 8 is 15. 15 take away 4 is 11. We're good. Everything checks out. We're good. We verified that this is true. We verified that that formula that we learned in the beginning of class works. Okay, the next example says to find the number of elements in this big ugly thing. This is a ugly set here. It says take A union B and intersect it with C. Take A union B and intersect it with C. What is that going to look like? Luckily, we just did A union B up here. We have C given right here. So when we talk about the intersection of those two things, like we're talking about what do they have in common, right? Let me actually show you what we're talking about. A union B intersected with C would look like this. A union B is, we just did that, right? It's right here. Let me write that down. And we're trying to intersect that with set C. What does set C look like? Well, it's given to us right there, A, E, I, O, U. So A union B is right there. C is right there. We're trying to intersect those two things. What does that intersection look like? So we need to talk about the elements that are in both of them at the same time. Remember, that's what intersection means. The overlap, where do they overlap each other? I think it's A, E, and I, right? You see the A is in both of them, you see that E is in both of them, and you see that I is in both of them. So I think they intersect with those three letters. A union B intersected with C results in this set right here. The question is asking, what is the number of elements? How many elements is in that? That's what the question is asking. My answer is going to be a number. This is not my answer. My answer is 3 because there are 3 things here. So when they put this in right there, that means tell me the number of elements in this thing. Now, of course, you probably want to find the thing like we did so that you can count the number of elements. But this is not my final answer. My final answer is 3. So same thing on the bottom one. My final answer is going to be a number. The final answer is going to be the number of elements in this thing. Now, very similar question, but that one says union and this one says intersection. So when I'm talking about A intersect B and then intersected with C, What does that look like? Well, A intersect B, we actually did that up here, right? So luckily we already have that D, E, F, G. And set C, of course, is given to us as A, E, I, O, U. So when we're talking about A intersect B and then intersected with C, we're talking about this set intersected with this set. And remember, intersection means what do they have in common? Do they overlap each other? There's only one thing they have in common, and that's E. E is the only letter that shows up in both of these two sets. There's an E here, there's an E here. E is the only thing. But that's not my final answer. My final answer is 1 because there's one element there. And it's asking you for this. It says the number of elements in that thing. Well, here's that thing. It only has one element. Okay, so be careful. Like what I often see, like a common wrong answer, I'll ask a question like this, and then someone gives me an answer of this right here. It doesn't make sense. Like this question has to be a number answer, like 1 or 5 or 12 or 20 or 0 or something like that, right? This doesn't make sense to give an answer as a set when it's asking for the number of elements in the set. Okay. For our next example, it says we're given the number of elements in set A is 610. We're given the number of elements in set B is 440. And the number of elements in set C is 1,000. Also, we're given that the number of elements in the universal set is 2,900. You move my camera a little so we can see a little more of this page here. When we're talking about the universal set, we are talking about the whole rectangle. Remember U, when we use the letter U to represent a set, we are always referring to the universal set. And that's the whole entire Venn diagram. So all the stuff on the top is given to us, but also notice there's some other stuff given to us. So these 4 things in red are also considered as given. And our job is now to just fill out the rest of the Venn diagram. That's what this means. Let me make it clear in a problem like this. For example, when it says 310, we do not mean in this case that the number 310 is in that area. We mean there are 310 people in this part. When it says 780, I don't mean the number 780 is one of the elements here. What we're meaning in this problem is that there are 780 elements in this part of the circle here, and so on. So when some people see the number of elements in A equals 610, I often see a lot of people just go write 610 right here. That is probably not correct, because when it says the number of elements in A equals 610, it means the whole circle must add up to 610. It doesn't mean there's 610 that goes right there. It means that this number plus this number plus this number plus this number has to add up to 610. Likewise, when it says the number of elements in set B equals 440, sometimes I'll just see people put a 440 right there. It's not what that means. It means the entire B circle adds up to 440. It means whatever that number is plus 310 plus whatever that number is plus 94 must add up to 440. And similar for the C circle, when it says the number of elements in set C equals 1,000, it means the whole C circle adds up to 1,000. It means 110 plus 780 plus 94 plus whatever we put there must become 1,000. And I think we should start with that one. Notice the C circle is the one that's almost done. The C circle has 3 of its 4 parts, right? 1, 2, 3, 4. We're just missing that middle part. So I think we should do the C circle first, right? I think we should take the fact that there are 1,000 elements in the C circle. That means that 110 plus 780 plus 94 plus whatever that middle number is going to be. When I put that question mark, I'm referring to that right now. It means all that stuff has to add up to 1,000. That's what that means. So if you take 110 plus 780 plus 94, you get an answer of 984 for that part. So 984 plus whatever that middle number is going to be must add up to 1,000. At this point, you should just subtract 984 from both sides, and you will get that that question mark needs to be 16. We now know there are 16 people in the middle right there. Now that we have that, I think we could go deal with the A circle or the B circle, because the A circle and the B circle both have 3 of the 4 parts, and we're able to find the missing part. Like let's for example look at the fact that the number of elements in the A circle is supposed to have 610. The only thing I don't know is this part up here, but I know the other 3 parts. So I can say 110 plus 16 plus 310 plus something adds up to 610. I could say 110 plus 16 plus 310 plus whatever goes here. I don't know what goes there at the moment. Adds up to 610. I'm putting question mark. You could put X there if you want. I mean, same thing. Okay. So if I take 110 plus 16 plus 310, I'm getting 436. 436 plus something has to equal to 610, right? So this already takes up 436 of them. There's supposed to be 610 total, so whatever I put here needs to be the rest of them. You can figure that out by subtracting 610 minus 436, and we are getting 174. So that question mark, which is referring to this, is telling us there are 174 people over there. Now the A circle should be adding up to 610. The C circle should be adding up to 1,000, and then the B circle also has to work out correctly, right? Remember the number of elements in the B circle was 440, or it's supposed to be 440. I'm still not sure about this part. So let's add up the things that we do know in the B circle. We know that 310 and the 16 and the 94, right? Those 3 are in the B circle, plus the missing part is supposed to add up to 440. So go ahead and add up the 310 and the 16 and the 94. That turns out to be 420 plus whatever that missing part is. That question mark is now referring to here. And you can subtract and you'll see that we get 20. Okay. We are not quite finished, though. We've done some good stuff, but we're not quite finished. You might say, why are we not quite finished? Well, the one thing we have to check also, the number of elements in the whole universal set is supposed to be 2,900. That means when I add all these numbers up, it's supposed to be 2,900. Do I get 2,900? Let's go ahead and add all those numbers up. 174 plus 310 plus 20 plus 110 plus 16 plus 94 plus 780. That's supposed to add up to 2,900. It's not. What's going on? Remember, sometimes we have people out here that are part of the universal set. They're part of the rectangle, but they're not part of the circles. So if all the numbers I have so far adds up to 1504, then I better subtract 1504 from 2,900 to see how many people are left. There are still 1,396 people to be accounted for. Those 1,396 people are out here. Let me recap how we did that. All the people that were accounted for so far at this point had added up to 1504. But we knew that the whole rectangle was supposed to add up to 2,900 because that's what it says right here. So the difference between those is 1,396. We still had not accounted for 1,396 people. That just means they're out here. That just means they're not in any of the circles. They're part of the universal set, but they're not in set A, they're not in set B, and they're not in set C. In a survey of 1,000 investors, it was reported that 600 of them had invested in stocks. Sorry, let me fix this first. In a survey of 1,000 investors, it was reported that 600 of them had invested in stocks, 500 of them had invested in bonds, and 100 had not invested in either. Fill out the appropriate Venn diagram. So the basic Venn diagrams are usually labeled as A and B. Of course, in this case, we need to call it stocks and bonds. Okay. So the A circle represents the people who invested in stocks. The B circle represents the people who invested in bonds. It's a tough question. Fill out the appropriate Venn diagram. Well, I think what some people would do is say, well, 600 people invested in stocks. I will sometimes see people put the number 600 right here. That is probably wrong. When we say 600 people invested in stocks, we don't necessarily mean there's 600 here. We mean that this number plus this number adds up to 600. When we say that 500 people invested in bonds, we don't mean go put a 500 right there necessarily. We mean that this number plus this number adds up to 500. So I don't really know what to do with the 600 or the 500 yet. I know that these two numbers add up to 600, and I know that these two numbers add up to 500, but I don't really know what to put in there yet. I do know what to do with this 100. It says 100 people did not invest in either. That means 100 people were part of my universal set. They were part of the survey, but they did not invest in stocks or bonds. Those 100 people are out here. 100 people did not invest in either. But they're not going to be in the stock circle and they're not going to be in the bonds circle. There's 100 people hanging out here. They were in the universal set because they were part of the survey. They're part of the 1,000, but they did not invest in stocks or bonds, so they don't get to go in the circles. So I can definitely fill that out, but I still have 3 other things to fill out right there. Now, it is true that I still have 900 people to account for, right? Because there were 1,000 people that were surveyed and 100 of them did not invest in either. So I still got 900 people that I need to deal with, right? There needs to be like 900 more people that I need to put in here. These 100 people are out here, but the rest of the 900 are going to be in here somewhere. In other words, I do know that this number plus this number plus this number should add up to 900. I do know that. Remember the formula we learned earlier today. I think this is going to be a good application of it. The number of elements in the union of the stocks and bonds circles is the number of elements in the stock circle plus the number of elements in the bond circle minus, because we might have double counted some people, the number of elements in the intersection of the 2 circles. We learned that at the very beginning of class today. In fact, we had that at the bottom of the very first page today. That was also, if you remember, in the notes right here. That's called the inclusion-exclusion principle. And here's a good visual of what we're talking about right now. When I'm talking about the number of elements in the union of the 2 sets, that means anyone anywhere in these circles. How many people are anywhere in these circles? And we know it's 900. We just figured that out because there were 1,000 not in the circles. So there's there were 100 not in the circles. And there's supposed to be 1,000 total. So the other 900 are in the circles somewhere. But that's what the union is. The union is that plus that plus that. Number of people in the union is this number of people plus this number of people plus this number of people. That makes up the union. We know that has to be 900 because we know there's 100 out here and we know everything's supposed to add up to 1,000. So we still have 900 to account for somehow. We also know the stock circle itself has 600. That means this plus this makes 600. We also know the bond circle itself has 500. That means this plus this makes 500. Notice I just double counted this middle part twice. So that middle part, which maybe we're not sure what it is yet, that was double counted, right? That's why the minus thing is there. I know this is a tough question, and it's our first application of this, or one of our first applications of this new formula here. But I hope that makes sense, right? I know there's 900 left to be accounted for. This plus this plus this must be 900. But this plus this plus this is also the number of people in the union. I know the number of people in the stock circle is supposed to be 600, the total circle, and the number of people in the bond circle is supposed to be 500, the total circle. Of course, I counted these twice. That's why it says minus there. I'm not sure at the moment how many are there. That's why I put a question mark, but we can solve for that question mark right now. Because we know that 600 plus 500 is 1,100. So 1,100 minus something becomes 900. You can actually just do 1100 minus 900 to see what's left over. Means there's 200. It means there's 200 right here. There's 200 in the what we were calling the question mark, which was the intersection of the two circles, which is the middle part. We know that's 200 now. We also, though, know that 600 people are supposed to be in the whole stocks circle, but 200 of them are right here. That means the rest of them are over here. In other words, I can say, since the number of people in the stocks circle equals 600, let me call that question mark now. Question mark plus 200 is supposed to equal to 600. That plus 200 is supposed to equal 600. You can, of course, just take 600, take away 200, and you will see that that question mark on the far left side is 400 now. Where the stock circle was supposed to add up to 600, now it does. We're good there. The bond circle is supposed to add up to 500. Let's make sure that turns out right. So the number of elements in the bonds circle is supposed to be 500. The only thing missing is this part on the right. That question mark plus 200 is supposed to be 500. If you take 500 minus 200, you will get 300, and now we are finished. So that final question mark, which is the far right of the B circle, is going to be 300 people hanging out here, and now we are done. Notice everything is accounted for. It says there's supposed to be 1,000 people total. 400 plus 200 plus 300 plus 100, that's 1,000. It says there's supposed to be 600 in the stock circle. 400 plus 200, that makes the 600. It says we're supposed to have 500 in the bond circle. 200 plus 300 makes that. And finally, there's supposed to be 1,000 outside of the circle. I'm sorry, supposed to be 100 outside of the circles, and there is. It's a good application of this formula called the inclusion-exclusion formula, or the inclusion-exclusion principle. Zoom out a little bit here. We are given that the number of elements in set A equals to 10, and the number of elements in set B equals to 7. What is the maximum number of elements that we could have in the union? What's the most amount of people I could have in the union of the two sets? That's what we're being asked in part A. And then part B says, what's the minimum number of elements in the union? What's the smallest amount of elements that could be in the union of the two sets? And then part C says, what's the maximum number of elements in the intersection? That means the middle part here. And part D says, what's the minimum number of elements in the intersection, which is the middle part. So remember, the intersection is the middle part. The union is this plus this plus this. And the number of elements in the union is this plus this plus this. That's what we mean when we're talking about that notation. The number of elements in the intersection is only the middle part. Let's actually start with part E. I know that's kind of a strange place to start, but let's start with part D. What's the minimum number of elements in the union, the intersection of the two sets? What's the least amount that I could have in the middle here? Is there a way to have 0 things in the middle? I guess. I mean, you're not going to get any less than 0. I'm going to argue we could end up with nothing in the middle. How could that happen? How could there be nobody in the middle? Nobody in the intersection? Well, that just means the 10 people that are in set A are all over in this part. And that means the 7 people that are in set B are all over here in this part. That makes sense? Like we could certainly have 10 people over here. I'm just going to draw little people, right? 1, 2, these are little people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 people right there. There's 7 people over here. 5, 6, 7. Those are little people right there. And notice I didn't put anybody in the middle. There are 0 people in the intersection. Of course, that's the minimum. You're not going to get any smaller than 0. We can't have negative people anywhere. And so 0 is the answer for sure to part B. But by doing that, I also maximized the union. Look at this same picture right here. By minimizing the intersection, I also maximized the union. I have 17 people represented here, right? There are 10 here and 7 here. 10 plus 7 is 17. There's no way you're going to get more than 17 people involved here. There's only 10 in the A group and 7 in the B group. 17 is the maximum number of people we could be discussing here. So my answer to part A is actually 17. There's no way you're going to get more than 17 people here. You can't have like 18 people, for example, because there's only 10 people in this group and 7 people in that group. So we're not going to have more than 10 plus 7. We maximize the union by minimizing the intersection. We maximize the union by not putting anybody in the middle, by having nobody in the overlaps. And similarly, let's go to this other Venn diagram because these two questions kind of go together. What if I want to maximize the intersection? That means I want to put as many people as possible in the middle there. How do I do that? How do I maximize the intersection? What's the most amount of people I could put in the middle? Um, I don't think I can put all 10 people in the middle. I know there's 10 people in the A group, but I can't put them all in the middle because whatever I put in the middle is also in the B group, and the B group only can have 7, right? But I could put 7 in the middle. Watch. 1, 2, 3, 4, 5, 6. I could certainly put 7 in the middle. I don't think I could put any more in the middle because the whole B circle is only supposed to have 7, and I've already maxed that out. The A circle is supposed to have 10, and I can do that by just including the other 3 right there because the A circle already has 7. Now they have the 10. Notice I have maximized the middle part. I have put as many people as possible in the middle. So the maximum number of people that could be in the middle is 7. And 7 is just the smaller number out of 10 and 7. This picture maximizes the intersection. It puts as many people as possible in the intersection in the middle part. It puts 7 of them. It just means those 7 that are in set B, all of them also happen to be in set A. And then there's 3 other people that make up the rest of the 10. But at the same time, while we were maximizing the intersection, we were also minimizing the union. Like this is the least amount of dots I could have drawn this picture with. There's only 10 dots here. That is the larger of 10 and 7. when you're answering a question like this is always going to be zero. You can always draw it so there's nobody in the middle. This is always going to be the smaller of the two numbers. This is always going to be the larger of the two numbers. And this is always going to be the sum of the two numbers. So we're basically asking this, what we're basically asking here is try to draw it so we have as many dots as possible, but still satisfying this. And then over here, I was trying to draw it so we have as few dots as possible, but it's still satisfying both. In other words, if this was the math club and the chess club and they were going to go on a field trip, under this circumstances, we only need to buy 10 tickets because everyone in the chess club also was in the math club, and then there was just the other three. But in this circumstance, I would need to buy 17 tickets because there was no overlap in the math club and the chess club under this circumstance. I know in our actual math club, chess club example, we had three in the middle. I'm just saying, what if we had different amounts of people in the clubs rather than what we were looking at in the beginning? So when you are asked a question like this, the maximum number in the union will always be the sum of those two. You will always be able to say zero for the minimum in the intersection. And you always take the larger of those two numbers for the minimum of the union, and the smaller of those two numbers for the maximum of the intersection. That is it for this section. Thank you for watching.